And on in the last lecture, we introduced the concept of a boundary layer, right? It's for the external viscous flow, and basically you see that if it's a viscous flow, flow above surface, solid surfaces, right? And a thin layer, a very thin layer, will be formed close in the region very close to that solid boundary, to the solid surface. And we only see the velocity gradient inside this small layer, this thin layer. And in another word, right, because we only have the viscous stress due to the velocity gradient, so we only see the viscous effect inside this thin layer. Okay, and this thin layer we call the, we give a name called the boundary layer. And outside the boundary layer, right, we're seeing that the region there is no velocity gradient, so there's no viscous effect. Okay, and we're just seeing that the flow is a free stream inviscid flow outside. And the boundary layer, we also seeing that it will keep increasing its thickness, right, along the place direction. And in the beginning, it will be laminar flow. And if the plate is long enough, okay, and the flow inside the boundary layer can become turbulent. And how we make that determine which position, at which region is laminar and which region is turbulent boundary layer, is determined by the local Reynolds number. Okay, and the local Reynolds number, we see local is that because that this is a function of x, the local location of x actually defined here. And we also have a critical value for the flow over the flat plate. This is the critical value, 10 times 10 to power 5. Okay, and from this critical value, we can find this critical location where this large U is free stream velocity, and rho and mu is the density and viscosity of the flow. Okay, so based on this critical Reynolds number, right, we can find where this critical position will be. And on the left-hand side of this critical position, we just thinking is at laminar flow, and on the right-hand side, we're thinking it's turbulent flow. Okay, so this is how we determine it. And similar to internal viscous internal flow. Okay, in this class we only focusing on the laminar part. Okay, we only focusing on the laminar flow because turbulent flow is a bit too complicated. Okay, and it's still active research topic nowadays in academic. Okay, it's not the scientists did not really fully understand the turbulent yet. Okay, so at the end we will still introduce the turbulent boundary layer, qualitatively. Okay, not quantitatively. Okay, we're just talking about that what's the basic fundamental difference between the turbulent boundary layer and the laminar boundary layer. Okay, and after we introducing this concept boundary layer, right? We also introduce another concept called the boundary layer thickness at the end of the last class, right? So basically that we want to know that where this dashed line will be, right? So that to separate this flow between this boundary layer region and the free stream region. Okay, and this y coordinates for the points on this dashed line, we call it the boundary layer thickness. So we have several ways, okay, to define the boundary layer thickness. Okay, so most straightforward way is just using the velocity. Okay, because we are seeing that from the boundary layer definition, okay, inside the boundary layer we have the velocity gradient. Outside, velocity is no velocity gradient. Everywhere will be the free stream velocity. So you may be thinking that maybe we can find a velocity u, right, at some location y, so that at this location, at this y location, the u will become big, large u. But mathematically, we cannot find that point because that this u, with this small velocity u, will approach this free stream u asymptotically. Okay, so that you cannot find that exactly at which location this small u will equal to u, because that you can always find that u maybe equal to 0.99 u, 0.999 u, 0.99999 u. Okay, depend on your accuracy. Okay, you need to make a decision that at which point, is acceptable. So usually people doing that using this 99% law. So basically, we're seeing that we define a boundary layer which is called the disturbance thickness. Sometimes we also make it straightforward, just call it the velocity thickness. Okay, delta. So it's defined as the y coordinate, such that at this y location, your u velocity will become 99% of the free stream velocity. Okay, so this is the first way we define the thickness of the boundary layer. Okay, and we also have the other way. Okay, the second way is called the displacement thickness, delta star. So what does this mean? This simply means that because that we knowing that from this velocity profile, we knowing that the velocity inside the boundary layer actually will be smaller than large u, smaller than this free stream velocity. So we can thinking that from the mass conservation's viewpoint, so the existence of the boundary layer, their net effect is just like to try to reduce the mass flow rate, right? To reduce the mass flow rate of the flow over the plate. Because if there's no boundary layer, right? So you integrate from 0 to infinity everywhere with large u for the and times density, you get the mass flow rate. But with the boundary layer, you have to integrate this small u times density over from the y from 0 to infinity, right? So it's obviously with the boundary layer, actually your mass flow rate is reduced. And we try to find a small distance like a delta star such that this effect of reducing mass flow rate is just equivalent that you move your plate vertically up with some small distance delta star. Because that we know that if you move the plate up, right, so that if you still from 0 to infinity, actually you remove some mass flow rate. So this region mass flow rate you reduce will be equal to the same region, the mass flow rate reduced due to the existing boundary layer. Basically, is that because rho is constant, right? Basically, if you integrate this area u velocity on y, so this area will be equal to the area here. Okay, and so based on our calculation, we found that for this delta star, which we call the displacement thickness, it can be defined in this way. Delta star can be 0 to infinity, or it's still accurate just from 0 to delta, 1 minus u over u dy. Can define delta star like this way. Okay, so this is the second definition, and the last one, the last definition is called the momentum thickness theta, and the idea for the theta is similar to the idea for the delta star. So because delta star is from the mass conservation point of view. So the momentum thickness theta is from the point of view of momentum conservation. So we can just also see that, because the velocity is reduced inside the boundary layer, so it also actually reduces the overall momentum, x direction momentum of the flow, right? So the net effect of the boundary layer will be just similar on the momentum, on the loss of the momentum, will be just similar to that. If we assume that this plate we also try to lift this plate on the positive y direction by a small displacement theta. Okay, so that this the distance rho times u square. Okay, this area here will be equal to this rho of u large u here. Okay, this is the momentum reduced in this boundary layer. Okay, and so by that way, okay, we can also define a new this momentum thickness theta. Okay, so this is the final result for it. All right, and it looks like comparing with the displacement thickness delta star, that we only have one additional this u over u coefficient of in the integrand. Okay, so this is where we left at the end of the last lecture. Okay, and on the textbook we have an example problem, to play with this definition of the boundary layer thickness. Okay, and please take some time to read this one, so we will quickly go through it. Okay, so for this problem, you may feel a little bit confusing because that this chapter we are talking about the external flow, right? But for this flow, actually, the channel flow is an internal flow. Okay, but the idea is that we can just assume that in the cases that if this L is very large, okay, if so this is a rectangle, this is square channel, okay, and we will assume that this side length, this channel width, okay, L is very large, okay, and in the region close to the entrance point, we can just assume that we will try to develop in the boundary layer on each all of these four side plates, okay, and assume that this L is much larger than the boundary layer thickness, okay, and so that the major region inside this flow inside this the flow inside this channel will be the inviscid flow, and we only have the shear stress, the boundary layer, in the region very close to the wall, okay, and we have two section points here. Okay, on the first section, we know that what it is the displacement velocity displacement boundary layer thickness will be, what this free stream in this region, right? What the velocity will be. And on the section 2, we only know the delta 2 star. We only know the displacement thickness. Okay, and you see that on the point 2, actually, this displacement and thickness developed a little bit further. Okay, it's a little bit thicker than the point 1 and section 1. So it's a question asking us that to calculate what is the static pressure difference between point 1 and 2. Okay, so this problem is a little bit tricky because that you need to realize that the major flow, okay, the major flow inside this channel is still inviscid flow, right? Outside the boundary layer. Okay, so with the inviscid flow, we can apply the Bernoulli equation, right? Remember that the Bernoulli equation we learned in the chapter 6. It's for the inviscid incompressible flow, right? So we can apply the Bernoulli equation for the steady state flow, inside this region, and so this will be the Bernoulli equation. P at the point 1, right? At section 1, P1 over rho plus V1 over square over 2 will be equal to P2 over rho plus V2 square over 2. Okay, let's assume that there's no elevation difference. C1 is Z2, okay, so they can cancel out. So the question asking us that we need to calculate P1 minus P2, right? We want to know the pressure difference. So from the Bernoulli equation, we can see that if we want to calculate the pressure difference, we need to calculate the velocity difference, V2 minus V1, right? So this is P1. So just organize this Bernoulli equation, right? And we know the U1, but we do not know the U2. That's the problem, right? So we know the we know the one velocity at section 1. We do not know the section at 2. We know the U1. We do not know the U2. So we need to find out what is U2. All right. So this is how we calculate the pressure drop. Okay. And on the left-hand side, we make this pressure drop dimensionless. Okay. So it's just divided by a constant value. So how we find the U2 to solve this problem? And because the major region, right, it's just still with our, just know that our assumption made, right? This L is much larger than delta star. Okay. So we can just calculate the velocity through the continuity. Okay, just assume that in this inviscid region, in this inviscous flow region, right, their continuity is conserved. So we have U1 times A1 will be equal to U2 times A2. So what is A1 and A2 will be? This A1 A2 will be that the area inside this dashed line, right? The area inside this dashed line. And remember that the width of this dashed line is equal to L minus 2 delta star, right? So that, at A1, we know that what is area A1, right? So actually A1 can be calculated L minus 2 delta 1 star square. And and A2 that can be calculated as L minus 2 delta 2 star square, right? So with this equation, we can calculate U2 from U1 because we know delta 2 star. Okay, just using this ratio. So substitute this U2 value you get from this continuity into to here, you get this result. Okay, and so it's showing that the pressure drop can be calculated directly from this delta 1, delta 2 star. Substitute the value into it, you can calculate what the pressure drop. Okay, so this is one example problem. So this example problem just helping you to understanding, okay, the flow structure, to help you to understand that, okay, for the flow over flat plate, it can be distinguished into two regions. Inside is viscous flow, outside is invisible. Okay, and also remember that this example problem is just give you some approximated solution. Okay, because that when we try to calculate the continuity, right, we only calculate the continuity in the invisible region, right? We're using like a U1 times A1 equal to U2 times A2. But we also have the flow rate inside the boundary layer. Although that because that in this problem, we assume that this delta star is much smaller than L, so that the mass flow rate inside this region is very small. Okay, so that's the reason we can neglect it when we calculate the continuity equation. Okay, but with this assumption, okay, the result we got here is only approximating the result. So be aware of that. Okay, so with all this concept of boundary layer and with this concept of boundary layer thickness, and now is that because we're focusing on the laminar flow, right? For the laminar boundary layer, so what is really this delta will be, right? What is the velocity profile will be? So two questions. So if you have a laminar boundary layer, so what is this delta will be? And what is this U velocity profile will be inside the boundary layer? What is U of function Y will be? This is two questions we want to answer. Right? How we do that? So we're starting from the Navier-Stokes equation, because that this is Navier-Stokes. We know that the Navier-Stokes equation is the equation to governing the viscous flow. Okay, and the special thing for this boundary layer is that because this boundary layer, this flow pattern, right? So we can make some assumptions try to simplify the Navier-Stokes equation. Okay, first thing, okay, let's assume that the flow is steady and two-dimensional. Two-dimensional means that we only have the y and x and y direction. On the z direction, there's no variation on the flow behavior. Okay, and also we assume that is incompressible flow, and both rho density and mu viscosity is constant. Okay, and also let's assume that this thickness delta is much smaller. The boundary layer thickness delta is much smaller than the plate length L. This larger L is the plate length, overall plate length. And also that we assume that in the free stream, right, in the region inside this free stream outside of the boundary layer, we assume that this U is a constant. U is not changing on x direction on the outside, and also that the pressure on this x direction in the free stream region is also not changing. The P, okay, dp parallel P, d parallel dp dx on this x direction outside of this boundary layer is also not changing. And with these all assumptions, okay, and we can simplify the Navier-Stokes equation. And the detailed procedure how we simplify it is a little bit above the scope of this class. So we will not give this in this class, but this will be the result. Okay, with all these assumptions, your Navier-Stokes will be reduced to this form. So this is the continuity equation, and this is the x direction momentum. The y direction momentum is gone because that with all this assumption, when delta is much smaller than L, usually the v will much smaller than u, so you can neglect v as those kind of things. Okay, and so this equation this is a simplified Navier-Stokes equation based on all this assumption for the laminar boundary layer. So it has a name. It's called the laminar boundary layer equation. Okay, it's called the laminar boundary layer equation. So it's just a simplified version of the Navier-Stokes equation in this for the flow, for laminar boundary layer flow. Okay, all this assumption is only valid for this laminar boundary layer flow. Okay, and also we have the bound. So this is a two partial differential equation for two unknown, right? We do not know u, we do not know v, right? Two equations for two unknown, and we also have the boundary condition at y equal to 0. Okay, so this is the y. This is, so at y equal to 0 is the wall, right? At the wall, we have no slip condition, right? Both velocity u, velocity and velocity will be 0. Okay, and y go to infinity, when y go to very far away from the plate, we know that u will become free stream velocity u. Okay, in the region very far away from this plate. Okay, the u velocity will become larger u, and also that at that point we will not see any, when y go to infinity, we won't see any u direction variation on the y direction, right? Because everywhere looks like u. So we have this two PDE, coupled PDE, second order PDE, and with this boundary condition. So can we solve u and v? Right? We can solve it. At this point we can using some computer codes to solve it numerically. Okay, but there is another way. Okay, mathematically we can try to directly, to simplify, try to derive, some things called the exact solution. We try to, instead of solve this numerically, we can try to solve some, this problem analytically in some kind of way. Okay, how we do that? Because that is usually analytically, very hard to solve this kind of equation. A coupled second order PDE, partial differential equation. Okay, it's very hard to do that. So we need to, do some math on, manipulation, so that to further simplify this form, to in some other form that we can more easily to solve, analytically. How we do that? So the first thing we need to realize that, after, actually in the boundary layer, right? So let me go back here. For the flow inside the boundary layer, right? Actually, that at different location, x location, right? Yeah, because this boundary layer thickness is different, right? So their velocity profile is also looks. So this u should be both a function of x and y, right? So because that, on the x direction, this delta is changed. On the y direction, it also has the gradient. So u should be both a function of x and y. But one thing people can assume is that this u function f of xy, right? So this is, let's assume that this is f1 of xy, and this is f2 of xy for the u at this point and u velocity at this point. Okay, let's assume that their shape maybe is similar. Okay, it all looks this profile, so this profile, it just looks like a scaled up of profile like this one. And this scaling up is based on this delta x. So this is delta 1, this is delta 2, right? So this is thickness 1 and this is thickness 2. So we can assume that this shape, they are the profile of this u velocity, they are similar here. So this is something we can assume. And whether or not this assumption is valid or not, we can verify later on by comparing the result we get from this assumption with the real experimental data. So if with this assumption, we try to develop some solution, and then we compare this solution with experimental data, it's agree very well. That means that this assumption is valid. If not, then that means that this assumption is wrong. Okay, let's assume that this shape they are similar. Moving from this one location to this location, it just like this scaling, scaling a delta on the y direction and also corresponding, scaling a delta x on the y direction. Okay, so with this similar, so this is called the, so this assumption, okay, we call it the similarity. Okay, so we assume that this large u, this small u over u, this velocity profile is similar for all values of x when played, when plotted versus a non-dimensional distance from the wall. And remember this non-dimensional distance. This non-dimensional distance, so which value we need to do this non-dimensionalization on the y? We just using delta to do that non-dimensional on the y. Okay, so in another word, in the MEC survey, how we write this similarity is like we assume that this u or this large u is only a function of g of eta, and this eta will not dependent on x anymore. Okay, so this eta will be independent on x. Okay, and this eta will be just like you do the y and what I see. How I explain this? So we can just assume that this eta will be approximated to y over delta, right? Because that is similar that this profile is similar that when you're plotting this value, right? Plotted versus a non-dimensional distance from the wall. So this will be y over delta will be that non-dimensional distance there. So u of u is only a function of eta, right? And so there is a guy, okay, his name is Blasius, and he developed this whole theory, okay, in I think in 1920 something, okay, 1920 something, actually, and he developed this whole theory, okay, and based on some previous researchers, result he got before for the, and he just assumed that this eta is this value. Okay, assume that this eta, because this is the proportional to this one, right? And this delta is a function of x, okay? So this eta also should be, a function of x, both y and x. Okay, and he assume that this is the eta value. Okay, again, okay, this is just assumption. And if with this assumption we get some result, and this result showing good agreement with experimental data, then means this is correct. Okay, so this is eta value he assumed. And he assume that u and this small u over this large u is only a function of this one. Okay, and also, okay, because that if you're taking a look of these two laminar boundary layer equation, if you're focusing on this one, the first one, so this is the so this is the incompressible continuity equation, right? So because that this is the force flow rho equal to constant, right? And so when we have the incompressible flow, and we can, first thing we can do is that we can try to introduce the stream function psi. Okay, remember the stream function psi we introduced before for the incompressible flow. So this is the incompressible flow. So with this psi, we can define the u as partial psi partial y and v with minus partial psi partial x, right? So this is the from the definition of this stream function. And why we define this stream function? Why we introduce this one? Because that when we introduce this stream function psi, this continuity equation will automatically satisfy, right? So because that if you put this u equal to this one, v equal to this one into here, you will see that this equation will be automatically satisfied. So by introducing this stream function psi, we can instead, before we need to solve both two equations, right? After we introduce this psi stream function, we only need to solve one equation because this one will automatically satisfy. So we simplify the problem from two equations to one equation. Okay, so let's introduce this one, and so this is u and v, and you substitute this, how we see. So let's also define, okay, dimensionless stream function, as a function of eta. Okay, let's define dimensionless function like this psi. Why we define this dimensionless stream function? Because that we know that this psi is a streamline, right? And we are seeing that this velocity profile has this similarity things, okay, on different x location. So similarly, okay, for the stream function, because stream function defines the velocity field, right? Your velocity field you have this similarity things. Your stream function will also have that this similarity thing. Okay, so in another word, your stream function can be also try to link with this this is eta, which is called the similarity variable. Okay, so let's define this dimensionless function so that we can link this so we can link this dimensionless stream function with this eta. Okay, will be in this way. Okay, so after define this one, so your psi will so this will give you psi equal to f of eta square root of mu xu, right? So you substitute this psi into u and v into this one and here. You can define what is u will be and what v will be. Okay, so this u is a function of large u times df d eta. This v is also like this way. Okay, and with this u and v, and if you look in this, because this is the equation we only need to solve, right? So now we know the u and v. We also need to know partial ux, partial uy, partial u square, partial y square, right? So from this u here, you can also calculate each term, partial u, partial x, as this one as a function of f, partial uy as a function of f, and partial square u, partial y square as a function of f. You substitute all these things, this one, u and v, into this momentum equation. You do not need to substitute into this continuity equation. Why? Because that continuity equation is already be satisfied from the definition of the stream function. So this is the only thing left. So substitute all those 5 things into here, u, v, and partial u, partial x, partial u, partial y, partial square u, partial y square into it. Okay, substitute everything here into the momentum equation, and this is what you get. The final result you get. So what does this mean? I go through very complicated this math procedure, right? And this part is not required for the exam. Okay, so if you get lost, do not worry about too much. Okay, but the basic idea is that by assuming that this velocity has some similarity, this shape has some similarity on different x location. Okay, and by then we can define this similarity variable, and by introducing the stream function, we remove the continuity equation. And also let's assume this stream function also follow the same similarity variable. Okay, and we substitute the things from this one stream function, we calculate the u and v, we substitute everything into the momentum equation, and all our previous problem will reduce to this equation. And what is equation? What's the difference between this one and the previous one? Previous one we need to solve this two, right? So this is a coupled second order partial differential equation. And now we only need to solve this one. So this is a only single third order ordinary differential equation. So this is not a partial differential equation anymore. It's only ordinary differential equation because the only independent variable is eta. Before, the independent variable is x and y, right? But now is only independent variable is eta. we reduce the problem from 2D to 1D. Okay. So in another word, after all this mathematical manipulation, we make the second order PDE equations, okay, two equations be transformed into a single third order ODE. And similarly, okay, because that we can write U and V as this in the form of F, okay. So we can also change this boundary conditions in the form of F. So for this equation, we can also have this boundary conditions here at eta equal to 0 at the wall and at eta equal to infinity with this one. Okay, so this is a third order ODE with three boundary conditions, right? 1, 2, 3. We have three boundary conditions. So we can solve it third order ODE. We can solve this exactly. Okay, but usually it's very complicated. To solve it, purely by hand, definitely it's very hard, right? So let's assume that we can still solve this numerically using some computer code. Okay, so we can try to solve that what is F as a function of eta, right? We can solve that what F as a function of eta will be. So this is the result of what you can obtain by solving that third order ODE. Okay, so this is definition of the eta we gave before. This is similarity variable, right? And so this is F on different eta value, and this is F prime, and this is F prime prime. Okay, and based on the definition of F, right, and it can be shown. It can be shown. Okay, actually, so this is the result we have. Okay, with this table. Okay, with different eta with the F. After knowing F value, knowing the dF dy. Sorry, dF d eta. You know that dF d square F over d eta square. Okay, you substitute the result you get obtained here, right? You can get the U value and V value. This is U, right, as a function. So U will be large U times F prime. So this is F prime. So actually you can calculate that U and as function, this U velocity as a function of eta. And you substitute this eta, with this definition here. You can calculate what the U as a function for both x and y. So you get the result U velocity profile. Right? So this will immediately this one will give you the velocity profile. Right? Because that with knowing that U over small u is df eta, right? So we know that from here we can find that just substitute this one thing back to this equation here. You can find that U as a function as y. You can able to find what the velocity profile looks like in the laminar boundary. So now we answer the first question, right? You remember we have two questions here, right? So what's the velocity? So what is the velocity profile in the boundary layer? We solve it from this table. So this is the velocity profile looks like, right? All this one. And the second question is that what is the boundary layer thickness, right? And so we have three boundary layer thickness definition, right? So let's look in the first one. The first definition is from the velocity profile, right? Where this U over large U become 0.99, 99%, right? So we can find that at that location Y will give us eta, Y equal to delta. So if you're looking here, so this is U over large U, right? F prime. Remember this one is this result is we obtained from here. Okay, U is over U is this one, right? So let's say 0.99, 0.99. So this one is showing that at eta equal to 5.0, your velocity U or large U will be close to 99%. Okay, so in another word, eta equal to 5, right? So what's the definition of eta? Eta is this y square root U of mu x, right? So which means that delta square root u over mu x equal to 5, right? Just replace this y. Whatever. So replace this y with delta, because that as this eta equal to 5, this y is the location where the delta will be 99%, right? And from this way, we can solve the delta. So it is showing you that delta will be 5.0 over u divided by mu divided by x. And if you multiply x on the both top and bottom, you can rewrite this as, delta will be 5.0 x. Okay, you multiply by both x on the bottom will be u times x divided by mu. And this is the Reynolds number, right? So this will, on the bottom will be square root of local Reynolds number. On the top, we will be 5.0x. So at the end, okay, we can rearrange this solution in this way. Delta as a function of x divided by x will be 5.0 square root of Reynolds x, Reynolds number of x, based on x, okay? So this telling us that what is the boundary layer thickness looks like, okay? So remember that, remember this definition of Reynolds x equal to, again, okay? This Reynolds x equal to rho ux over mu, right? And this rho over mu give you the dynamic viscosity. You can also write this as u of x, ux of nu, right? So this you have, remember that in this Reynolds number definition, you have one x here. So here, so this square root of Reynolds number x is a proportional to square root of x, right? And also on the top, you have another x here. So yeah, at the end, this telling you what? Your delta is in the order for x over 1 over 2. Right? Your delta of x, your boundary layer thickness is in a profile of this square root of 1 over 2. So that is why that when you see the boundary layer, their profile looks like this. Delta of x. And if this is the x. So this profile is increasing, right? With this speed, x over 1 over 2 in the laminar boundary layer. And after you find this delta result here, right? And you can just substitute your velocity profile again, okay? You can substitute this u or u here, this velocity profile, into the definition of this, the other two, right? In the definition of this theta, right? You see the theta involve this u or u, 1 minus u or u, right? Just replace the u or u with this f prime, df or d eta, right? And similar things for the delta star, replace the u over u as that, f prime here. And also you need to change the y to the eta, okay? And when you do the integration, you can also do that, and the result will be, also showing you that if you try to using the calculate the displacement thickness in this laminar boundary layer from this exact solution, and this will be the result. And if you want to calculate the that momentum thickness, theta, in this laminar, so this will be the result. And if you're looking at all these three, right, you will see that not only delta is proportional to the square root of x, this delta star theta is also same thing. Theta is also proportional to x1 over x over 1 over 2. Okay, no matter which boundary thickness definition you use, you're using delta star, or theta, their profile is all proportional to x over, square root of x. They're, this increasing with x, definitely increasing with x, right? And this speed of this increasing with x is proportional to this one. And also you can find that, the coefficient is different, right? So this is for delta, this is delta star, and this is 0.9964, right? So this coefficient is larger than this one, and larger than this one. So in another word, So relatively, so if you compare all these three boundary layer thickness, you will see that this is delta x. Something here will be delta star, and something at the bottom will be theta. So with the same location x, which means that with the same location of Reynolds number x, actually delta x will be, it looks like the delta I will be larger than delta star and larger than theta. Okay, although we have three ways to define the boundary thickness, right? So this is the thing I want to know. So this is how we calculated them. Okay, you need this in the exam. Okay, write this on your cheat sheet, and we also have one practice exam problem for this. Okay, to use this equation. Okay, give you that how to calculate the boundary layer thickness. All right, and so you need to know that all these three equations. You also need to know that this delta star, this theta, their growth rate is proportional to x square root of x, and you also need to know that delta will be larger than delta star, and delta star will be larger than theta. So all this is we develop all these three things based on this solution here. Based on this solution we got here for f, which we solve this exact solution. Okay, and again, okay, you do not really need to, to able to derive all this yourself. Okay, to derive from here how you make this similarity analysis, so that we can, change from the 2D problem to a 1D problem, and also that how we introduce the string function, so we can remove the continuity equation, so we only left the momentum equation, and in the end, we make this two second order PDE to a single third order ODE, and we can solve it, and we get all this result. Okay, so the procedure to how we derive to, from do this maths derivation is not really required for the exam. Okay, the important thing is this result we got. Okay, for this laminar boundary layer with this exact solution, how you can calculate their thickness. Okay, and also, okay, with this velocity profile we have, right? So this gives you the u as velocity, right, as a function of eta actually. And we can also try to calculate what's the wall shear stress, right? It will be calculated at mu times partial u partial y at y equals 0, right? And now because we know that u is a function of eta, right? So you need to use a chain rule. Partial u partial y will be equal to partial u partial eta times partial eta partial y, right? And this partial u partial eta, you get it from f prime here. And this partial eta partial y, you get it from the definition of this eta. Partial eta partial y will be square root u mu x, right? So by doing this way, you can calculate tau w will be equal to this one. Okay, and calculate this require partial second order f as eta. So you need to using this rule, and this is the result you need. F prime prime is this one. This is f prime prime, right? D square f d eta square is f prime prime. At eta equal to 0 is this one value, 0.3321. So that's why you got this 0.332 here. So tau w equal to this is 0.332 times this u, and also this u and and this is mu, right? Mu equal, and this is small nu, and we know that there are differences between the density, so they can cancel out, and there will be density left. Okay, and it will be equal to this one. You try to rearrange this one, it can be read in this form, because that this inside here is the Reynolds number. Again, it's square root of Reynolds number, and so this is how we calculate. You can calculate. So for the laminar boundary layer, right, from this exact solution. So this is what the wall shear stress value will be. It's also a function of the local Reynolds number, depending on which x location you have, where it is, and Usually, okay, we would like to write this tau w in a dimensionless format. So we define that shear stress coefficient CF. So this is the non-dimensional parameter, dimensionless parameter. Okay, so this CF will be equal to tau w divided by 1/2 rho u square. This u is the free stream u. You substitute this one into here. So this is you get. So shear stress coefficient CF will be 0.664 square root Reynolds number x. Okay, so from this exact solution, we obtain three things, okay? First thing, from this table, we know what the velocity profile looks like. Second thing, we can calculate what the boundary layer thickness looks like. And third thing, we can calculate what the wall friction will be. Right, all this one. And one interesting thing you need to realize that this CF equal to 0.664 over Reynolds number x. This theta over x, 0.664 over Reynolds x. So this one is same. So in other words, CF equal to theta over x. Right? You see that CF will give you this one, right? But from our previous one, we also know that theta over x is also equal to this one. So you actually for the laminar boundary layer, we do have this condition. And this is not a surprise. Why? Because that what is CF? CF telling you the friction force, right? So this is something related to force. And what is theta? Theta is called the momentum thickness, right? So this is something related to the momentum. So force related to momentum. That's true, right? Newton's second law. And the details how this is why this is true, you can read it from the textbook if you're interested. Okay, in the section 9.3, but it will not include in this class. Okay, but you do need to know. I just want to be aware of this. Okay, this CF, this equation actually is exactly the same with this theta over x. This equation. Okay, and there is a reason why they are same. Okay, and no, I will not introduce this in this class. Okay, and here we finish the introduction of this exact solution for the laminar boundary layer. Okay, so basically, we do some math calculations, so that math manipulation, so we can try to obtain this exact solution. And with this exact solution, we obtain some important flow parameters for this laminar boundary layer flow. And one last thing, okay, all the results we obtain here, this boundary layer thickness, this velocity profile, this friction coefficient, they are only valid for laminar flat plate boundary layer. They are not valid for the turbulent laminar flow. Okay, it's only for the laminar flow. Which in another word, okay, if you want to use this equation, you need to verify that the location you want to calculate these properties, that the local Reynolds number must be smaller than this 5 times 10 to the power 5 to make sure it's really a laminar flow, so that you can use those equations. Okay. So this is a laminar boundary layer, and we have another example problem to practice this flat plate exact solution, and it's a very straightforward one. So I would like to leave it to read it yourself. Okay. So basically, the idea is that just you try to using this table, okay, to calculate different quantities. Okay, to calculate what's the delta star, to calculate what is the V value. Remember, and calculate what is the streamline, will be equal to V over U, what this value will be. Just that the idea is just try to apply the solution you get is this table to calculate different quantities. Okay, so try to read this one yourself. Okay, and as I mentioned, right, we're only focusing on the laminar boundary layer. But if the Reynolds number, local Reynolds number, is larger than 5 times 10 to the power 5, the boundary layer will become turbulent flow. Okay, and for the turbulent flow, the things become very complicated. Okay, all the equations we had before, we derived before, for that Bloch solution, exact solution will not be valid anymore. Okay, so in another word, the velocity profile will look in the turbulent boundary layer will look different than the velocity profile in the laminar boundary layer. The boundary layer thickness of the turbulent boundary layer will also be different than the laminar boundary layer thickness. Okay, as well as wall friction. So here I just want to give you some, qualitatively, speaking. Okay, I want to let you know something. Okay, the first thing I want to let you know is this: is that usually, okay, the delta of turbulence, not usually, okay, delta of turbulence will be larger than delta of laminar. So this is the first thing you need to know. Okay, so when the flow after the flow become turbulent, okay, so turbulent. So with the similar Reynolds number, right? With that, so if you try to still using all this the equation here to calculate the boundary layer thickness for the turbulent boundary layer, actually the value you calculated here will be underestimate your turbulent boundary layer thickness. And that is why that if you look this picture in the very beginning of this class, you see that after the flow becomes turbulent, right? Actually this you see that there's a jump on the thickness here. Okay, so that is the first thing I want to let you know for the turbulent boundary. Okay, and it's and from the intuition, from the general, so from the common sense, okay, it's kind of easy to understand. Why? Because that the boundary layer we are talking about before, that boundary layer is where the viscous stress is important, right? Where the those viscous force is important. And we know that the turbulence is more chaotic, right? So in another word, turbulence has more strong capability to transport the things. Be careful about the word I'm using here, right? So turbulence has stronger capability to transport the things. What these things? It either can be the momentum, or can be the energy, or can be entropy, whatever. Okay, so that's why is that when the things become turbulent, it's also much easier that you transport this viscous effect to a further region, right? Because that has strong transport effect things to transport the thing, right? And that is why that the turbulent boundary layer is thicker, because that it can affect more region. Okay, so this is the thing that I want you to know. And the second thing I want to know, for the turbulent flow is that the velocity profile. So this is what the velocity profile looks in the laminar flow, right? And for the turbulent flow, the velocity profile will look different than this one. And what is difference? The difference is that from here, right, you're seeing that for this laminar flow, right, it will take like this distance. It's like take this distance, like try to. So if you try to calculate this velocity slope at y equal to 0, so maybe not seeing this one. So we look at this part u, part u, part y at y equal to 0. This slope is this angle. Let me write this theta of laminar. And if you also can look in the turbulent boundary layer profile, you will see that the slope of this part u, part y at y equal to 0 is this small angle theta of t. So theta of t is much smaller than theta of l. Okay, so in another word, okay, in the laminar flow, the speed in the turbulent flow, okay, the speed of this velocity changes. Okay, in a very small region, this velocity changes a lot in the region close to the wall in the turbulent. Comparing to the laminar, it's also a small region, but this this gradient is not that big. Okay, so this in another word, this telling you that this partial u, partial y at y equal to 0 for turbulent is much larger than partial u, partial y at y equal to 0 for laminar. So this quantity here is larger than this quantity here. And we know that this quantity will give us tau w, right? because tau W equals mu times partial U partial 1. So in another word, the tau W of turbulence is larger than tau W of laminar. Okay, which means that the turbulent boundary layer has more wall friction than the laminar boundary layer. Right? So, and this is also very easy to understand from the common sense. Why? Because we know that the laminar boundary layer, the flow structure is more organized, right? More, layer by layer, more smooth. And the turbulence boundary layer is more chaotic. And when you have the flow very chaotic to running on a plate, and comparing with the flow very smooth and running on plate, definitely this is has generated more friction than this one, right? So, two things I want to know, okay, for this turbulent boundary layer, the difference between the turbulent boundary layer and the laminar boundary layer. First thing, their thickness, okay, turbulent boundary layer tend to have a larger thickness, boundary layer thickness than the laminar boundary layer. Second thing, the friction, wall friction in the turbulent boundary layer is larger than friction in the laminar boundary layer. Okay, so that's something I want to introduce to you. And here we finish the whole contents of this class. Okay, and again, okay, the last two chapters, chapter 8 and chapter 9, for the internal and for the internal and external compressed viscous flow, we only cover several sections. Okay, we didn't cover everything on the textbook. Okay, so that you need to, use my lecture notes to see that which chapter is covered, which chapter is not covered. Okay, so keep this in mind. And so everything will be done. Everything is done here, and the only thing left is for the final exam. So the final exam time is on the syllabus already. Okay, on the syllabus, the exam time is on December 17th. Okay, it's Thursday. Okay, 10 days later. Okay, it's on Thursday, and between 2:15 to 5 p.m. Okay, so we have 2 hours and 45 minutes for the final exam. Okay, the final exam will be cumulative. Okay, and so which means that 50% okay, will be the contents after the midterm 2, which will be chapters 6, 7, 8, and 9. This will take 50%. The content for the first midterm, chapter 1 to 3, covers 25% of the exam problem. And chapter 4 and 5, which is the content of the second midterm, will cover another 25% of the final exam. And we will have like around 40, to 50 multiple choice problems on the blackboard. Okay, it will be closed book, proctored by that lockdown browser, and also using the web camera. So again, okay, you are allowed to bring a piece of cheat sheet, and one piece of scrap paper is also allowed. And please, okay, use the practice exam I posted on the blackboard to practice this to prepare your final exam. Okay, and I make all three practice exam available now. Okay, the first two is the practice exam you already done before for the midterm 1, midterm 2. You still can use them to to prepare for the contents beyond chapter 1 to chapter 6, chapter 5, between chapter 1 and chapter 5, and the practice exam for the final exam, I only give you the problem for the last 4 chapters. Okay, so using that final practice exam to prepare for the contents between of chapter 6 to chapter 9. All right, and grading I remember I talked about this before, right? So it's grading. If everybody doing very good, so I will not curve the grade. But if everybody is not at good, I will curve the grade so that you know, the class mean will be between B and B plus. Okay, so that so it's most likely from what I see based on what you guys did in the first two midterms, it looks like I need to curve the grade. Okay, so yeah, another word. Okay, your final grade depends on your relative position in this class. Okay, and any other questions, guys? Before I finish.
I had a quick question about cheat sheets. Are we only allowed one piece for the final?
Yeah, I really do not. Yeah, you know, I think one piece of paper is enough because that for some contents you only need to copy important contents. Okay, some other things like those unit conversion factors, those flow properties, you really do not need that because that I will make sure that I will give you everything in the exam. Okay, I will make it clear
I
in the
was just
exam. Okay.
wondering if we'll be allowed more since we're covering more chapters on this test rather than the other two midterms where it was only two.
Yeah, but you can use in the both sides, right? For one piece of paper, so you basically like two actually. I really do not think you really need that much because that uh from you know, you already have the first we already have two midterms, right? You see that those midterms actually most of the problems, right? Like if I have 50 multiple choice problems, it's almost like a 2/3 of them actually it's just conceptual problems, right? You really do not need to use the equation a lot for the things. Okay, so I don't think you really need more than one piece of cheat sheet to copy out to copy. You just need to copy important equation. That's my suggestion. Okay,
Okay.
you really do not need to copy everything. Okay, it's not very that efficient. Okay,
Okay, thank you.
no problem. And also my suggestion is that uh, because a lot of problem is the conceptual problems, and there those conceptual problems is also where the people are easily to make the mistake. Remember that for the first midterm, a lot of students make the mistake of this you know, gauge pressure and you know, absolute pressure, you know, that 1 atmosphere difference, right? And also that you know, something like you know, be careful about that in the second midterm, you know, for the thing what I say, um for those you know, fluid kinetics, right? Kinematics, right? And those kind of things, you know, was translational motion, rotational motion, uh, normal deformation, angular deformation, all those kind of things. Okay, so you know, focusing on this basic concepts, right? So that be careful about these small things that you do not make the mistake. Okay. Any other questions, guys?
Professor, I had a quick question. So
Sure.
you said that 75% of the final is going to be more geared towards the last couple chapters we've been going
No,
over.
no, I think we already, I think the TA, right, already sent an announcement, right? So the final exam, 50%, 50, half, okay, half percent will be toward to the contents after the second midterm. So which will be chapter 6, chapter 7, chapter 8, and chapter 9. And chapter 8 and 9 is a short chapter because we didn't cover everything. Okay. So this will cover 50%. Another 50% will be separated by half. 25 will be for the content of first midterm. 25, another 25 will for the second midterm. Okay, so yeah, in other words, you can just think that the other 50% is for the things that will be before the midterm, well, before the second midterm.
Okay, that makes more sense. Thank you, Professor.
No problem. I will, don't worry about this, okay? I will write you guys an announcement on the blackboard to, you know, to confirm the exam date, the format of the exam, and what the contents, you know, what the coverage content required for the exam, okay? So if there's no question, I will just finish today's lecture. So at the end of this semester, okay, I think maybe this is the last chance you know, last time I have the chance to talk to you. So I just thank you for everyone. You know, I think you guys cooperate very well in this class. It's not very easy to teach this class, especially this class is very big, right? We have a lot of students. It's a huge class actually. It's not very easy to, you know, to teach this class in this, you in this current situation, right? We have to teach it remotely. So thank you everyone for the cooperation. I think you guys do a good job. And so just try to we still have 10 days for the final. So try to prepare earlier. Try to put a time on to prepare for it. And if you have any question, I still hold my office hour this Wednesday and the next Wednesday. Okay, so if you have any question, feel free to talk to me. And if you are not able to go to my office hour, you are also feel free to write me an email. Okay, so there's no issue for me. And so I will just finish here. Yeah, before that, we also have a attendance quiz, for today's class. So it should be available now. Go to the Blackboard and try to finish that one for today's attendance. Okay. And so that's it. Okay. Bye, everyone.
Have a good day, Professor.
You too. Bye.
Thank you, Professor.
Bye. Yeah.